Alright, hell yeah, go. We're gonna debunk the mold effect in under 3 minutes. Alright, so this is what that do. You pull on this rope like at 5 miles an hour. Holy Toledo, we're pulling on this rope at 5 miles an hour. And guess what? This part of the rope ain't moving. You know what I mean? Let's do that one more time. You're like, what the hell are you doing? You know what I mean? You're pulling on this rope. Well, look, there's pieces of this rope that aren't moving. You know what I mean? Like this piece hasn't moved yet, and now it's moving 5 miles an hour. Okay, so it's not moving here. It's moving 5 miles an hour here. So guess what? This chunk of rope from there to there is changing, is going from 0 to 5 miles an hour. It's changing its velocity. What do we call that? Acceleration. So it actually takes a force to change, so that's the tension in the rope. You know what I mean? Once I got this rope up to speed with constant velocity, yeah, the only mass, the bits of mass are just right in here that are changing. Okay, so keep that in mind. I don't know if that helps us at all, but here's what I'm getting at. This is why the mold effect takes place. Why it doesn't, and then I forgot to put them in here, you know what I mean? But why doesn't it just go over a lip? Even if you have a smooth lip, you know what I mean? Maybe you have like a pile right here and it's going over just like a nice smooth circle. Why doesn't it keep in contact with the circle? You know what I mean? The entire time. Why doesn't friction here just hella? And why does it sprout up like a fountain? Well, here's why. Is because, let's say I drop this little bead, or rock, or whatever, it's just one of these little chains, and drop it right here. What's the velocity right there? Is 0 before I drop it. What's the velocity right here? Hella. So velocity, hella. Okay, now we're getting somewhere. So when the chain fountain does its thing, let's say even if it doesn't hop, let's say this doesn't hop at all. You created the lousiest chain fountain in the world. You made it out of stuff that's too heavy. It ain't even popping up. But anyway, it's still falling to the ground and it's still pulling all the chain out. We can agree with that. Well, guess what? The velocity, and it's a continual process because now it's hitting the ground and then it's piling up. But now guess what? Here's the secret sauce. What's the velocity like right here? This is V hella. But guess what? What's the velocity right there? That's also V hella. So this is why the mold effect works, is because guess what the velocity right here is? This one is 0. Velocity is 0. So here's your change. So here's your mass of chain that's changing velocity. And it's not a very big mass, you know what I mean? So it doesn't take that much force. So just a little force to actually get this crap to move. Yep. And, I need to pause this video. Damn it. I caught myself. Said something unnecessary. Totally unnecessary. Doesn't matter that, yeah, we get it. There's not much weight there. That's not the point. The point is, well, let's say there is hella friction here. Who cares? You know what I mean? It keeps this from going to hella to infinity. You know what I mean? To hell yeah. We're going to break space and time. Okay, so yeah, this ain't V8 sideways. This is V hella. Isn't this right here V hella too? Hell yeah, hell yeah. At some point, you know what I mean, this chain is 0. You know what I mean? At some point. But you know what I mean, it kind of like starts to move like a snake. And then let's say V hella is right there. So now what am I getting at? Damn it. It's like when your brain is made out of mushrooms and you're just like, damn it. Alright, more time on the clock. Alright, hell yeah. We're back. We ain't doing this in 3 minutes, but we got it. So, yeah, let's say this is the last bit of chain. Well, you know what's going to happen. It's got so much velocity, because it's got velocity, hell yeah, that this thing is going to go sky high and whip. So, you know, this thing is going to be like right up here very soon as it whips up and out of this thing. You know what I mean? So yeah, it's definitely going to whip, and it's probably like whips over here. Because this mass of this chain right here is just real small. Mass velocity is small. The mass part's the same, but this is big M, same V. Same V, you know what I mean? So the inertia is crazy. All right, let's take a pause. Okay, it's not super quick on this one, but this is where I want to go with this. And so it all comes down to this little radius right here, you know what I mean? This is a little circle with a small r. And yeah, this chain will maybe get to about here, you know what I mean? Because this is the circle, and it probably won't whip this high, but whatever this tight radius is, this is the part that's going to whip, and it's going to whip hell yeah. It for sure is going to whip, and it's going to go over here too. Okay, and it's because, yeah, so it's such a circle problem. Negative m r omega squared. This is force is equal to mass times acceleration. This is the mass. This is the force on this, and it's totally what's trying to wing all these little beads in all directions. And it's trying to do the same thing even to this bead. But this bead is being pulled down by this whole system over here. So this bead can't just fly off. So this bead kind of acts as a pivot point, and that's why this whip really whips out. And that's the same thing with crack the whip. Crack the whip is a circle problem, and velocity does help because this is your inertia. This is your energy. Whatever your mass of this whole thing times your velocity, for sure, that is, see, huge mass, good size velocity on just a really tiny circle, little mass. And then even if we add the chain back in here and pile it in, this mass don't count, you know what I mean? Because it's only pulling up like one ball at a time. So the only mass in here is still real small. And if this mass is real small, these balls that are flying out in this direction, so let's say there's 5 of them, the force on those due to centrifugal forces are what's lifting this part of the chain. And so I'm going to conclude that. And because the aspect of the chain fountain, we can just kind of get rid of everything now. The aspect of the chain fountain is you're already starting with like a sharp radius. You know what I mean? So it's actually kind of easy. Well, no. There is enough friction here that if you just let this spill over, it kind of takes a little while to get started, but it will. And but it is easier if you. I don't know how I can prove that in under 2 seconds, but it is easier for a chain fountain to start by initiating. You're initiating velocity, and you're initiating a pretty decent arc, which does 2 things. Because look at this. No, this proves that too. F equals ma, and the a is negative r omega squared. So your a is, well, I'll just write it in. So mass r omega squared. So if we have a large r, we get a bigger force in the upward direction. If we have, oh, no. These are the things that are going to, oh, let's see. Oh, this is so, never mind. This thing is so backwards because it's got a negative sign. So let's put our beads. These beads want to fly this way. I think we get it. They want to fly that way. And they do so with negative r omega, r omega theta. Sorry, mass, radius, omega. So those are the units. So if you increase your velocity, so if you just have a bigger v, like hell yeah, that thing double v, you quadruple the force that wants to fly these pieces off. You want to induce the whip effect and just lift this rope off of whatever it's on, whether it's this lip or if it's just trying to hold its shape in air. Do we have enough time for this? Okay, at least we're boiling it down to like what the hell actually matters, because there's so many. It's like a bicycle. There's so many complex things that you can just point to like one thing and be like, ah, that's it. Okay, and then if your radius is large, so if you increase this, that helps. You know what I mean? The thing is going to lift. If you increase the radius, that helps. You increase this. if you increase the mass, I don't know why that would help. And that's where I got confused, where it's just like, what? It's this. It's this. Is that the, so when you're on Earth, this is in, because it's all lopsided and backwards. But if you're on Earth, and the Earth is spinning, it's got that omega, it's got that, it's got a large R, it's got that, and a pretty tiny m, real tiny m. Oh, this is interesting, because if you reduce the radius, this is backwards. Yeah. If you reduce the mass and reduce the radius, I don't get why. Now I'm just kicking myself because like this is the omega, radians per second, and that's velocity basically. Because well, let's do it. So what's your velocity? Velocity is omega r. Okay, so then what's omega? Omega is velocity divided by r. Oh, yeah, so this is great. So yeah, so you got to put in that. So omega squared is velocity squared over r squared. So this mr omega squared goes to mr v squared over r squared. Okay, so yeah, you got mv squared over r. So there you go. So now, if you increase v, hell yeah, that helps. If you reduce r, hell yeah, that helps. So yeah, like this velocity, that's going to really help. Reduce r, that's going to help. So even though you're starting with a large circle, it's just to get that initial velocity going and to reduce friction on that point. Else you'd want to do a tight. You'd want to do a tight whip circle, not like a huge arc, because this thing's gonna like your chain fountain's gonna equilibrate to a pretty narrow R, pretty small R. But at least we did that. But it comes down to this. This is what's the lifting force. If you have V right here, you got that. If you got a small R, you got that. And then the mass of the chain is just these links. This link doesn't count because this is a pivot point. You know what I mean? So even just right here, this piece doesn't really count. You know what I mean? So even like here, like only 50% of this side actually matters, where the weight is just right here. Like literally, that's the M that you're pulling. So, obviously it doesn't help to increase this and this. You want these to be as light as possible, and then they'll go flying. It's just because if this is the Earth, weigh 160 pounds, and you're going to subtract, and this is omega, you're going to subtract this. It's going to be mg, which is 160, minus mr omega squared. So, hell yeah. And this is real small, because why is this small? It's because on the Earth, this is friggin' tiny. The radius is monstrous. But this takes 24 hours just to do one cycle. You know what I mean? So these actually just are real small, and it's only a fraction of your of weight. So it's only like 2 pounds. You know what I mean? So if you're on the equator, you'll weigh like you'll lose 2 pounds. That's all. But you are trying to get flung off. And if you how does this work? If you weighed... Oh. I don't know. It's an equal ratio, so it doesn't really maybe it doesn't really matter how much. Well, I don't know. That's a good place to stop. But holy Toledo, this is going to be a lifetime to actually get this down to like pretty concise. But thanks for joining me. That may be just part 3, at least a little shorter on the mold effect. My answer, part 3. All right, thanks for joining me, and that's a video.